And it gives me great pleasure now to welcome Manu. Manu has been really instrumental for the liaison between Europe and the US. But really key, again, as a community, because what we do is not Europe and US and elsewhere. It's really how we can establish ourselves as a scientific community globally. And I would like to thank him for traveling again, crossing the Atlantic again and again to be with us in presence today. Thanks so much, Manu.
Thank you for the kind words, Serge. Thank you. So I can use this just to advance the slides. Let me just, yeah, perfect. Thank you so much. Good morning, everybody. And again, some familiar faces, some new. So just real quick, by way of introduction, thanks again. Let me just start off by echoing what we heard from Serge. Thanks to the local organizing committee, Thanasis, the Slices team. I'm Manu Gosain from Northeastern University. Just a quick background, and I'll dive straight into what we're going to talk here. But I'm at the Institute for Wireless Internet of Things at Northeastern University, and primarily manage one of the flagship National Science Foundation investments in the US called PAWR, Platforms for Advanced Wireless Research. Basically, it's a distillation of very similar in spirit to what Slice's research infrastructure is attempting to do. However, it predates Slice's by about 4 years. We were started in 2017. So basically, over the next 2 days, I'm going to do a much deeper dive of what PAWR is, or talk about the end-to-end reference architecture piece, connect certain dots, and sort of give you a little peek into what the US academic community and industry are thinking about. So probably we'll have some nice twinning and some offline discussions as well. I wear a few different other hats. So outside of the academic community, I also engage with the US Department of Defense. So we'll be happy to sort of fold in what the US DoD is doing with 5G. And believe it or not, they're investing significant amounts of funding in building 5G and making it implemented in a military context. In addition to that, I also work with the regulators in the US, so with the Federal Communications Commission on their Technology Advisory Council, and that probably has more impact on spectrum. So any of you who operate digital infrastructure or are an industry partner operating real commercial deployments, spectrum is obviously a big headache, but it's also an opportunity. So we think of creative ways of unleashing spectrum, whether in the context of 5G, beyond 5G or 6G. And then obviously you saw all the little 3 or 4 letter acronyms of these open source, open access, open community consortia and alliances. And basically, I'm privileged enough to have a position there. So I can give sort of a little bit of a peek into how the thought process works. And then looking ahead, we sort of organize, and again, a shout out for those of you who might want to attend the 6G Symposium. So this was the first one that we kicked off in 2020. We were sort of first out of the blocks, and it was a little bit of a rocky start because we started to talk about 6G quite early, even though nobody really knows what it's going to look like. But, humor me as I sort of think through with you what 6G is going to look like, what are the fundamental technical challenges, what are the gaps, and how do we sort of move from 5G to 6G? So today, it's basically just going to be a high-level overview. Tomorrow, I believe I have a longer time slot to sort of get into more details of the infrastructure, talk a little bit more about how we are sort of thinking about the reference architecture question Serge talked about and how we're interacting and influencing the user community. Oh, sorry. No worries. No worries. But this room was able to hear probably, right? Okay, so I'll keep going. No worries. Main obvious question for all of us or most of us in the room is why open test beds in the first place? Why not just buy a commercial implementation or buy a commercial chipset and start working in your labs? So the main thing is we want to avoid technology lock-in. We want to impact interoperability, and we want to leverage what's happening in the standards bodies, primarily in providing the academic community a window or a peek into how standards are implemented. So for somebody who's a student or even a very well-funded, very well-staffed lab, building an end-to-end 5G architecture, a standalone architecture, is not an easy proposition. So the idea of having neutral, large-scale test beds with a professionally managed DevOps team was something that the National Science Foundation and US industry wanted to coalesce and come together for. So on the academic side, the idea was we had lots and lots of capacity, intellectual capacity, and experience working with SDR, software-defined radios, programmable FPGAs. We also sort of produce the best and brightest PhD students that then end up going into industry, and having them trained on real infrastructure is very important to quickly transition into an industry workplace. And then the idea that you have access to lower level layers, primarily the physical layer, scheduler, MAC, things that all of you want to work on for your algorithms, et cetera, was not necessarily possible with following the commercial curve. On the industry side, believe it or not, they also appreciated this notion of open test beds because it helped them shorten design cycles, connected them back into industry, connected them back into academia, and also sort of helped in this world of disaggregation and multiple different interfaces that have been defined not just by 3GPP, but by also the ORAN Alliance and Small Cell Forum and other areas to really keep track of how this is all going to go. So again, we wanted to coalesce every the industry and academia in form of a public-private partnership. Did you take the batteries out of this to put in this? No, we're good. Okay, so we came up with PAWR, right? So PAWR was basically founded in 2017. It was a dream of the National Science Foundation. They pitched in about $100 million US, half coming from government and the other half coming from an industry consortium of 35 member companies. And the goal was to build 4 test beds across the US, targeting certain technical areas, but also industry applications and verticals. And the whole hope was that these would be available to the academic community and to the industry partners for basically cross-pollination of ideas, for proof of concepts, as well as of development of different pieces of the software stack. And again, the idea was to be software first and to leverage as much as possible COTS infrastructure that would be end-to-end programmable. Sorry for the blurred image, but this is sort of for all the key players. Most of them are well-known names, but the idea here is these are all end-to-end on the telecom value chain, from chipset vendors to tower companies, and everybody saw value in contributing to a neutral, large-scale test effort. I'm going to get into way more detail and sort of talk about how you can leverage these test beds, what the lessons learned have been, what are sort of the major software building blocks of each. But given today I have a short time, just wanted to do a quick introduction. So 4 test beds, that's our portfolio, and a large-scale emulator, which I believe still to my knowledge is the world's largest RF emulator, called Coliseum. This was infrastructure that was previously built by DARPA for a Spectrum Collaboration Challenge, and then was transferred over to the PAWR infrastructure program and is managed and housed at Northeastern University. So these 4 test platforms are doing lots of different things. There's a wide variety. Some of it is orthogonal, and that's by design because each of these test beds is envisioned as an individual snowflake, meaning they're looking at a few different things and they're trying to sort of make an impact. PAWR out in Salt Lake City is working on end-to-end software-defined networks, as well as looking at massive MIMO. They work with Rice University and have a completely open source version of a massive MIMO 64TR system that's been deployed and basically gives you low-level access all the way from the physical layer. And again, any of you who worked on massive MIMO understand, measuring the channel, collecting large scales, IQ samples, doing real-time or near real-time processing, and calculating the channel matrix, et cetera, are quite important tasks, and mostly commercial equipment is not going to give you the bits to sort of change those parameters. But here you have access to that, and the nice part across everything you see up there, it's all remotely accessible, meaning sitting at your laptop, you should be able to log in, SSH into these nodes, instantiate software, touch hardware in real time, and set up topologies for experimentation. So that's in Utah. Cosmos, which again, I believe some of the folks here at the NETOS testbed are also well connected to, is run at Columbia University in downtown New York, looking primarily at millimeter wave in a large, in a dense deployment area in downtown New York, as well as looking at backhaul research in the optical domain. So they have ROADMs, which are reconfigurable optical add-drop multiplexers, which allow you to sort of transmit RF signals in the physical domain and do switching for faster timescales. So you now can actually capture large swaths of IQ samples at millimeter wave frequencies with large number of antennas and sort of switch them in near real time in the optical domain, and then have an SDN fabric controller on top of it. AirPow in Raleigh, North Carolina is our UAV and our high mobility test bed. So here you have fixed infrastructure in the form of commercial networks deployed by Ericsson, as well as complemented with software-defined radios. But the idea here is to primarily focus on UAV-based experimentation. Now, this is a little bit more challenging to do remotely. However, there is a much more sophisticated emulation system that they use, leveraging Coliseum, but also with one of our industry consortium partners, Keysight, which allows you to do large-scale emulations, and then permitting the resources available to the test bed, they actually can take this out into the field and actually fly UAVs, fly swarms. They have remote pilots in command. They have a large number of UAVs, and that is something that is very, very exciting for researchers. Last one, the youngest of them all, it's ARA. This was only funded recently in 2020, so this is still being developed. The ones with the green available today is the test beds that have been sort of fully or close to be fully deployed, including Coliseum, and that's all available for you. ARA is still being built, but the idea there is to close the digital divide and focus mostly on the X-Hall piece. So we're looking at mid-haul, front-haul, back-haul, and looking at a wide heterogeneity of radio resources from microwave all the way up to free space optical communication at 195 terahertz. So that's sort of our portfolio. As I said, I'll get into much more detail tomorrow when I have more time. So today, and then I just wanted to give you a sense of what people are up to, right? So this is basically infrastructure that is end-to-end programmable. The key places that we are seeing a significant amount of interest from the research community is obviously on the open source reference architecture and software development, on the UAV experimentation, IoT style experiments, and the most recent one on AI ML for wireless. So these test beds are out in the wild, meaning these are deployed on rooftops, on streetlight furniture, all across these cities and campuses, and they are collecting large amounts of data. So any of you who are working on AI ML know that data is the new oil, meaning it's a currency that you need to train all your models. And we've been collecting large amounts of data and been releasing those data sets, annotated, and these are all available publicly on our website that you can use to train your algorithms. So you will hear later on about ORAN, about the radio intelligent controller, as well as the AI algorithm. So you'll have a good idea of where these data sets can actually factor into your research. So this is all available completely openly. We're also doing a lot of work with spectrum management. So again, back to the DoD, looking at coexistence between commercial and military applications, leveraging the same spectrum. So that is something that we are also very actively in pursuit of and working diligently towards. I'll flash this slide. I'll get into more detail tomorrow. But the sense here is, again, what Serge said, right? So we learned very quickly as we started building those test platforms that we needed a benchmark. We needed something that would be end-to-end programmable, fully virtualized, and instantiated at turnkey, pace. So what we did is we went out shopping, looked at these open communities, open alliances, and basically realized that 3GPP actually does a pretty good job in defining standardized interfaces that can be leveraged. And since it's all standards compliant, you can pick different pieces from different vendors or different consortia. Now, the trick there is the system integration piece, the glue code, but that's what we believe that the digital infrastructure testbed communities can come together and have a standardized way of doing it. And then that could be used to leapfrog further innovation in terms of any subsystems or modules that you may want to influence or affect. Realize these are not, completely open source stacks that are up there, but the idea here is that leveraging what's happening in 3GPP, in ORAN, and other places, you can actually build this and then vet it with the community. So this was something that was published in 2020, got a significant amount of attention, and this is something that we have sort of instantiated and support both on PAWR and on Coliseum. In Notion, the idea is basically very simple, which is, leverage what's already out there. We're not trying to recreate the wheel. Again, we don't want to mess with what's happening on the standards curve, but think of this more as dual use. meaning if you're trying to do something commercial, if you're an industry partner, you can still use that same architecture, but you can swap in pieces based on what you're trying to do. So if your objective is around spectrum sharing, you need real low-level access down into the scheduler MAC. For spectrum sharing, you probably do want to lean more towards an open source stack. However, if you're trying to do something that is more proprietary, or you have your own millimeter wave phased array system, and all you need is something that has the scheduler, the MAC, or the ability to interact with your millimeter wave subsystem, you go ahead and work with an open access stack such as Radis's. Or in the case of slicing or security, some of the features in the open source ecosystem are not mature enough. But the idea is that this can all still be instantiated, even if you work on that spectrum of completely open source to open access to closed or proprietary. This one is on the O-RAN side. Again, I'm just going to pretend that most of you are aware of the O-RAN architecture. So the idea of a disaggregated radio access network with 3 elements, the CU, the DU, the RU, split across different functional splits between option 2 and option 8. With the O-RAN Alliance, we're looking primarily at option 7 to X, which is implementing the open front haul interface between the DU and the RU on your right. And the real key, which is the network intelligence part, which is the radio intelligent controller that's running as similar to an SDN controller at a layer which is a little bit higher from where the base infrastructure is. So now for the first time, you can actually bring in technical domain expertise for people who don't understand what the radio access network does, but they can start to build X apps, R apps, and sort of using the interfaces defined and agreed upon by the O-RAN Alliance community, such as the E2, the A1, the O1, can actually influence what's happening on the radio access network in near real time or in non-real time. So this is something that's going to be very impactful. This is an architecture that we do support on the PAWR testbeds. Again, take that with a grain of salt, because this is still a very evolving ecosystem. So we work both with the open source community as well as the O-RAN software community to instantiate open source versions of the RIC, as well as the open air interface stack for the disaggregated RAN piece of it. Here again, just trying to show a few different applications that we've been working on, primarily from the DoD side. But again, this also has a very strong impact in what academics want to do today. So very rich, if you are a PhD student looking for a research topic, this is something you may want to consider as well. And it's supported by the digital infrastructures that we have. Last but not the least, this is something that I think the US and the EU community can come together on, which is this notion of a cloud native implementation of any subsystem. So for us, across PAWR and Coliseum, our lowest common denominator, our piece of exchange is a container. So this is what we are trying to work towards, which is to basically build a Docker or a Kubernetes container or a Linux LXC container that fully instantiates the software piece. So whether it be the Gnode B, the UE, the core, the SMO, or the RIC, and basically release it with out into the community. So if you're an experimenter, you can start with this reference container, instantiate that on our test beds, twiddle the parameters, the bits that you want, and then reinstantiate it in a different test bed. So the way we like to think about this is a migration or a journey of a container where you started on Coliseum or your local lab, you sort of build it up, and as you want to test it up at scale, you're able to port it over to Coliseum. And I will, not pretend that this just works magically. There is a little bit of glue code. Any of you who worked with all the different messes of kernel versions and issues with Linux and Docker, etc., we have to solve those, but we've gotten pretty good at doing that. And then we're able to take that and validate that into a real world ecosystem such as PAWR or Cosmos. And the idea is to have sort of a feedback loop where we take this out into the wild, conduct experimentation, whatever lessons are learned, that software can be debugged, enhancements can be made, and then this container can move around. Now, why is this important? This is important because if you're sitting here in Volos and you're sort of working with a collaborator across the EU or in the US, you now have something where you can start from, and that's a common starting point. All of you have probably come across times when you're working with collaborators on trying to match or twin your setups. And or at the end of the day, something or the other is always different. So the idea here is somewhat of homogeneity, but also still giving you the parameters that you can play with as you sort of move towards your experimentation. I'll talk more about in detail, give you more specifics, certain examples, and then all the different SDKs, toolkits that we have released. I'll get into more of that detail tomorrow. I know I'm over time, but just one slide I wanted to flash around 6G and the timeline. So from a US perspective, we're working towards the IMT 2030 timeframe, which is where the community sort of in industry agrees that will be used and leveraged to define what 6G is going to become. But that's still 8 or 10 years away. These are sort of some of the things that, at least as an industry-wide consensus, the industry thinks these are important research topics to consider. So at the bottom are the radio interface topics. So if you are a physical layer geek, you really go out and you look at advanced modulation, code scheming, you look at terahertz, you look at joint communication sensing, full duplex communications. And if you're looking at it from an architectural perspective, you're looking at softwareized RAN, digital twin networks, integration of terrestrial and non-terrestrial networks, SATCOM, and that's sort of going to form the basis of 6G. But it's a journey that's going to be taken in steps. And the idea is the testbeds that I flashed earlier are going to become kind of a neutral arbiter of how these technologies will be evaluated, how these technologies can be dropped in, again, leveraging standard interfaces and being in lockstep with future and current 3GPP release cycles. So what I want to close with is sort of to talk about that the time is now. So I think this forum is a great forum to start to think about, especially given the pre-competitive nature of some of these technology areas. What we can do jointly, how these testbeds and digital infrastructures can help us, and then how do we sort of match and move towards that 2030, 60 timeframe, and sort of, this would be the first generation, I believe, and I think, you'll hear that later today as well, where academia and the open source community, as well as the digital infrastructure community, will be close to lockstep in terms of implementing and adopting features that are defined in 3GPP. So 4G, we were behind the curve. 5G, we were playing catch up, but in 6G, if we are able to sort of coalesce as a community, both on the EU and the US side, we should be able to have a greater impact. And I think people in this room will have a lot to do with that. So with that, I'll stop here. I know I'll be talking to you again tomorrow. Again, best wishes for a successful summer school to all. Thank you.